Hello, welcome to this 21st class of our physics of materials course. We have done a lot of analysis on the various material properties that we are interested in trying to explain, and in particular we have focused on the electronic and thermal properties that we can examine and record in a macroscopic sense, and we have tried to understand what is it that exists within the material at microscopic level or even at a sub microscopic level, and try to see what is the manner in which the phenomena that are occurring at those atomic and subatomic scales impact the property that we measure at the large scale, right. So this is what we have done. We have already looked at a couple of different models. We looked at the Drude model and the Drude-Sommerfeld model. Right. So between them we have already looked at how you can we have looked at the process first of all. So you are now become familiar with this process by which you can look at a material property and then attempt to build a set of rules and regulations that you can place on the constituents and see how those rules and regulations impact the property that you are measuring. So that process, which is itself I think a very important piece of understanding, is something that we have now gone through, right. So in future if you were to run into models which may be vastly more sophisticated, may involve a lot more concepts that are of interest for that system, you at least will understand how the process occurs, right. So there are different properties that people model, different systems that people model, and at least in general concept what we have done so far is the basic kind of approach that all of those models will take. The kind of computation they do may be different, the computational tools they use may be different, simply because the equations they put down may be such that specific kinds of computational tools may become necessary. It may not be straightforward for you to just write the equation and solve it in one go, right. So the complexity of the equations may change, and therefore the mathematical approach that you may have to take may change, and this is where a lot of the mathematics that you learn as in the form of engineering mathematics becomes useful to you. So you can find specific problems and find the appropriate mathematical tool which will enable you to solve the equations that correspond to that problem, or at least make plots of those phenomena and examine how those trends change as you go to one extreme or the other extreme of that of the experimental conditions. So this is something that I think we at this stage we need to pause and recognize that we have come this far, we have an understanding of this process. So so that is itself a very important aspect that we need to recognize. Over and above that, specific to our discussion, we have looked at two models. We have looked at one model, seen what predictions it makes. We have recognized that in fact it makes pretty good predictions, that it is able to do a lot of things that we didn't I mean at least upfront it feels like it is a very simple model because you are just taking something that belongs to a gas, employing it on a solid that contains electrons, and so upfront there is reason to be skeptical that such a simplistic approach may actually work, but in fact it turns out that it makes pretty good predictions. And as I said at the beginning, our whole purpose is to get away with the simplest theory that we can possibly use, right. So if there is a simple theory that works, there is absolutely no need for a more complicated theory. So only when we find locations and reasons why we feel that this theory that we are considering is actually not good enough, that we need to that there are specific aspects that where it fails, we end up having to look at more sophisticated theories. So we did recognize that there were reasons why this model was not good enough, that in fact it is making certain assumptions, and those assumptions sometimes are explicitly visible to us, sometimes in the equation we write it is implicit, and in that process somewhere down the line errors are creeping into the model, and errors are creeping into the equation which we do not realize. We simply write the equation because that equation is consistent with the rules we are assuming that the system is following. It's simply that when you take a step back and examine whether or not in fact those rules are actually being followed by the system, only when you do that you recognize that in fact that some of those rules are not correct for the situation that we are considering, some of the rules are not appropriate for the system that we are considering, and therefore even though the equation is correct with respect to that rule itself is not appropriate for the system that we are looking at, and therefore the equation that we are writing is not appropriate for the system that we are looking at. So you can do the calculation step by step correctly from there on, but fundamentally that equation was not appropriate, and therefore the result that you get is also not appropriate. So therefore we had issues with the Drude model, we recognized the issues, we were able to pin it down to the fact that at a very fundamental level, since we have assumed it is a classical particle, we used Maxwell-Boltzmann statistics, and that implies certain kinds of behavior for the electrons with respect to energy, with respect to temperature. Then we recognized that it needs to be modified, it needs to be improved, and such an improvement was brought about by Sommerfeld many years ago in the 1920s. So we looked at that improvement, what he had done. So he basically did not modify the model very significantly, at least in broad framework he still treated it in a very similar manner to what Drude had done, except he recognized that the particle system that we had behaved somewhat differently, and it was not appropriate to just arbitrarily apply the rules of classical mechanics onto these particles. So quantum mechanical behavior and more specifically the Fermi-Dirac statistics was appropriate for the system that was being considered. So he applied Fermi-Dirac statistics to the Drude model, and immediately it showed an improvement. More specifically, the specific phenomenon of property of specific heat, which is the and in our case we are looking at specific heat at constant volume, and even more particularly we are looking at the electronic contribution to the specific heat at constant volume. It turns out that if you compare the Maxwell-Boltzmann statistics versus the Fermi-Dirac statistics, we are able to see how and why the Fermi-Dirac statistics is actually able to correctly tell us or at least significantly improve the ability to predict the electronic contribution to the specific heat at constant volume, mainly because it shows us that the rule that the particles are going to be fermions and therefore follow Pauli's exclusion principle, and also the fact that there are fixed number of states at a given energy level, and therefore once they are full you have to move to higher energy levels. Once you place that rule on the system and therefore model the system and write the equations with respect to those rules, you find that naturally you reach a situation where only some number of electrons can participate in this temperature increase process. The fact that you significantly reduce these number of electrons that are able to participate in this increase in temperature immediately also means you are significantly reducing the amount of energy that is required for this temperature increase process, and therefore you are significantly reducing the contribution of electrons or the electronic contribution to the specific heat at constant volume. Okay. So this is how so we see that that it is not enough. So this is the thing that we have to be very cautious about. It is very easy to state a rule and then write the equations with respect to the rule and then continue solving. It is very important for us to always step back and check whether that rule that we have imposed is it reasonable, is it correct, are there reasons to think that in fact we should be imposing some other rule, okay, because otherwise in fact the calculations for the Drude model are fine, the calculations for the Drude-Sommerfeld model are also fine. So we cannot just simply say that the equations naturally lead to whatever solution they do and therefore everything is fine. The only reason the Drude model is failing is because the original rule that we are imposing on the system is itself not appropriate. So that is the important thing that we need to recognize. Fine. So from there we have come and we have found that the Drude-Sommerfeld model is much more appropriate and is able to do things that the Drude model is not able to do correctly. So that is a big piece of improvement that we have done. Now having come this far, we should also recognize that even as an improved model, the Drude-Sommerfeld model is also effectively what we would call as a free electron model. See, in its simplest form, as I mentioned, all it is doing is it is replacing Maxwell-Boltzmann statistics by Fermi-Dirac statistics. Almost all the other ideas, so to speak, of the Drude model are largely left undisturbed. So largely we are continuing to use those ideas. So what it means is because we are saying it is a free electron model, what it means is that as a system we are saying that the electrons are largely free to move through that solid and they are not really experiencing any differences in the potential that they experience from position to position as they move along that the solid. Okay. So when you have such a possibility, I mean, okay, at one level, as we mentioned earlier on, we can justify it in a loose sense, in the sense that, you know, for a given electron, if you take a particular electron that is moving through the solid, what it is going to experience is that there are a whole bunch of positive charges within that solid, which represent all those ionic cores, as I called it. Okay, these are the ions at crystal lattice locations. Okay, ions at crystal lattice locations. So, so these are the ionic cores. So, in our solid we have a framework of these ionic cores, ions sitting at crystal lattice locations, and we have an electron cloud that is around it. Okay, so free electron cloud. Now, if you have this combination of ionic cores which are now positively charged, and a free electron cloud which is negatively charged, and they are all sitting around the same region, we can make the approximation, or we can sort of think that it is okay to make the approximation that as an electron travels around, it is seeing a large positive charge and a large negative charge sort of competing with each other, and since both the charges are essentially the same, I mean, you have the same amount of negative charge and the same amount of positive charge, because they are not independent of each other, the solid is charge neutral. So these positive charges at those ionic crystal locations are because those ions have released one electron per location to this free electron cloud. So for every electron in this free electron cloud, there is a positive ion in the crystal location. So there is a direct one-to-one correlation between these two. They are not independent of each other. This cloud did not appear from nowhere. Okay, so and neither did these ions. They were all initially neutral atoms. Each of them released one electron. So it got, the atom became a positively charged ion plus one charge, and the cloud became negatively charged. Electron cloud became negatively charged with minus one electron charge, so to speak, released into the cloud. So there is a direct one-to-one correlation between these two. So the amount of negative charge you have here in this free electron cloud is exactly equal to the amount of positive charge you have in this ionic core, the collection of ionic cores, all the ionic cores taken together, fine. So therefore the approximation that we are making, that when an electron is moving along, it is not really seeing, it is seeing a net neutralized charge, so to speak, is reasonable from that perspective. We can say that there is a net, the net positive charge versus the net negative charge is essentially 0. We can make such an assumption, fine. So therefore at that level of argument or understanding, it is not, it does not appear that it is too wrong to think of it as a free electron model, where the electron freely moves around. It is not really seeing, there are no features in that potential. Okay, so the net potential, potential versus position is largely featureless. There is no higher potential at any one location, there is no significantly lower potential at any other location. It is largely featureless. It is largely so the electron has no preference. It does not have any preference to be at any one location. There is no reason to believe that it will move faster at one location, or it will get stuck at some location if it gets to that location, and so on. Largely it is featureless. So whatever happens at one location is the exact same thing that the electron will experience at any other location within that solid. Okay, so that is why it is on those grounds and that argument that we can say that when you say it is a free electron model, it is not very far fetched. It is reasonable, at least to start with. Okay, so that is how this has come about. Now the issue then therefore is that we have to, so as we see, this is not a bad assumption, and also as in terms of the values, this does not seem to be a bad assumption, because we are getting reasonable values, numbers are working out reasonably okay, fine. Okay, so so from both those perspectives, it is not too bad, it is actually okay, we are in the right direction at least. The problem with this approach, which we can immediately recognize, okay, is that if you take a real material, so some silver metal you take, or whatever it is, silver or copper or anything that you are measuring, we know for a fact from our general understanding of material science, materials engineering and so on, we know for a fact that many materials are anisotropic. Okay, many materials are typically anisotropic. What does it mean? It means isotropic material means that the properties are the same regardless of the direction. Okay, so in other words, you have a solid, you measure the property in the x direction, you will get a value, you measure it in the y direction, you will get the same value, you measure it in the z direction, you will get exactly the same value. Any other coordinate, any other line that you draw through that solid, you draw the line, you make measure the property along that line, you should get exactly the same value if it is an isotropic solid. Okay, so whatever the property you are interested in, you should end up with exactly the same value. Our experience is that a typical solid is typically anisotropic, okay, especially if you take a single crystal of that solid. Okay, if it is a polycrystalline sample, sometimes if all the crystals are randomly oriented, then as an average overall solid, the solid may appear isotropic simply because it is polycrystalline, and and you have millions of such crystals. If it is polycrystalline and the crystal size is small and your sample size is large, right. So if you have, so I would say this is single crystal, okay. Okay, so we have three cases here. We have a single crystal where and a polycrystal with a large crystal size and a polycrystal with a very small crystal size, relatively speaking. Okay, so we will just quickly draw this, then we can compare these. Okay, so we will just complete this diagram, so that way you will have all the crystal, I will just draw it here. Okay, so just for completeness we have it now here. So you do not worry about the shapes here, but basically it is a polycrystal with a very small crystal size. This is a polycrystal with very large crystal size, and this is a single crystal. In this, if when you say single crystal, what we mean is the atomic planes are oriented correctly from this end to that end. Correctly meaning in whatever sense, if this is a 111 plane, all the way down this side is also a 111 plane. Okay, so it is all exactly the correct atomic orientation is perfect, atom to atom the order is correct from this end to that end. So that is a single crystal. This is a polycrystalline sample with large crystal size. So these are individual crystals. So we only have 3 plus 2 5 crystals in this sample. Okay, in this sample we have only 5 crystals. Here there is atomic order here, but which is different from the atomic order, the direction of atomic order here. Okay, so this may be the 111 plane in this sample, that may be the 111 plane in the other sample, this may be the 111 plane in this crystal. This may be the 111 plane. Just to pick a plane, we just arbitrarily I am showing you the 111 plane, and we could have this as the 111 plane here. Okay, so we have this is a polycrystal with large crystallite size. This is polycrystal with very small crystal size. So the 111 plane could be in all over the place in each of these crystals. So like that we can have it, right. So now in a polycrystalline sample, when it gets more and more, when the crystal size keeps decreasing more and more to much smaller sizes, and therefore you have huge number of small crystals within this within the dimension of that sample. Then when you take the measure a property from this side to that side of the sample, which is a large sample, you have something in your hand which you can make a measurement on. When you make the property measurement, what you are seeing is sort of the averaged property of all these crystals, right. When you get to a single crystal, you are seeing a property that is very specific to this particular direction. So this, if you measure a property like this and you say all the 111 planes are here, then you get the property in specific to that orientation. Here, since the 111 planes are in all possible directions and therefore all the other planes are also in all possible directions, I have just picked 111 as an example, all the other planes are also in all possible directions. The direction of the sample has no real link to the direction of any set of planes within this sample, whereas the direction of this sample, this direction in which we are making the measurement, has a very unique orientation with respect to the orientation of planes within this crystal. Because there is only one orientation of planes here, this direction in which we are making the measurement is specifically oriented with respect to those planes. Here there are so many such crystals here that the planes are all over the place, they are pointed in all different directions. So when we pick one direction for making our measurement, it has no specific relationship to any one particular plane. This could be perpendicular to 111 plane in one crystal, it could be perpendicular to 110 plane in another crystal, it could be perpendicular to 132 plane in some other crystal, and so on, right. So what you see in this measurement is an average property across all possible planes. In fact, the smaller the crystal sizes, the more well averaged the properties, plus assuming that the crystals are all randomly oriented, that is also important, okay. So very small crystal size, randomly oriented crystals. Okay, very small crystal size and randomly oriented crystals, and that depends on how you have made the sample, because you can have a small crystalline crystal size and still have highly oriented crystals, meaning even though the crystal size is small, many of them have 111 direction in one particular direction, many of them, okay. So therefore that is not the example we are looking at, we are looking at small crystal size and randomly oriented crystals. If you take that combination, if you make a measurement this way, you will get a value. If you make the same measurement this way, you will get and you normalize it for the size of the sample, okay. So let's say conductivity or resistivity, not resistance, resistivity, if you measure it this way or you measure it this way, you shouldn't see a big difference, because the crystals are all randomly oriented and there are many of them. On this sample, even if it were randomly oriented, since it is a very large, the crystal size is large and you only have 5 crystals from here to here, when you take a measurement this way, on average there is greater orientation in a particular direction along this way and greater orientation in some other direction along this way, okay. And it just so happens that for many materials, when you have such an orientation, the property works out to be different, and that is what we are referring to as anisotropy, which you are aware of, okay. So anisotropy is the fact that if you measure a property in one direction, it will work out to be something different than the same property measured in another direction. Such a thing is usually very glaringly visible when you look at a single crystal, okay. So in a single crystal, since there is only one possible orientation of all the planes of any given particular plane, except maybe for the family of planes, a family may have some specific orientation with respect to each other, but in general there is orientation is what we are talking of, okay. That is why it is a single crystal. So it is very likely that a property measured this way is very significantly different from the same property measured this way, very likely, okay. It just depends on, by luck you may end up by chance you may end up with the same family of planes on both directions, in which case it will work out to be the same number, but in general this is not going to be true. If you take any two random directions, I just take the same measurement and measure it this way or this way, right. So I have any number of directions in which I can measure the property, as long as I can make connections to the sample in that appropriate manner and so on. So I have any number of directions in which I can measure this property, and if it is in a typical sample, all those directions will give me different values for the property, or almost all of them will give me different values. This will become a little less likely here, there is a little greater chance that you may hit upon the same value more than once, but still there is it's a very good chance that you will get different values here depending on the direction in which you make the measurement. Certainly when you go down to this kind of a sample where you have a very small crystal size and all of them are randomly oriented crystals, when you do that, in fact your values will work out to be the same, okay. So this is our understanding of what we mean when we say property is isotropic or anisotropic. In this sample the property is isotropic, simply because there are very small crystal size, they are randomly oriented, so they average out the property across all directions. In this sample the property is anisotropic, distinctly anisotropic. So from a purely material perspective, if you want to talk of, you want to understand the property of a material and not just the property of a sample, this is the way of understanding the material property. Okay, so here the material in its fundamental form, which is that single crystal, which has all the characteristics of the material are captured here, that the orientation, what kind of atoms are there, where they are located, how are they located with respect to each other, in what directions are the bonds, in what directions are the other bonds, all that information is well captured in a single crystal. When you go into a sample which is a polycrystal, you are sort of muddling up that information, you are mixing up that information because you have many particles pointed in different directions. So when you look at a single crystal and make a measurement, you get something much more fundamental about that material. Okay, the actual behavior of the original material is captured when you look at a single crystal. When you look at single crystals, say of silver, copper, any of those materials and a large number of other materials also, in general you will find that there is a lot of anisotropy in the properties. You measure, say, electronic conductivity in one direction, you measure it in another direction, they could be off by a marginal amount, they could be off by a significant amount. A classic example of where the property could be off in a very significant way is, say, graphite. Okay, so in graphite you have a layered structure. If you take a single crystal of graphite or well oriented graphite, then you will find that if the planes of graphite are arranged one above the other, planes, it has a planar structure, so you hexagonally bonded carbon atoms are there in each of those planes, and each such plane is called a graphene sheet. If you take those graphene sheets and organize them exactly one on top of the other and get a well oriented graphite sample, you will find that conductivity perpendicular to those sheets is very poor. Okay, conductivity parallel to those sheets is very good. So this is a very significant difference. It is not just a factor of 10% or 20%, it is a very significant difference. Conductivity perpendicular to the sheets could be negligible and conductivity parallel to the sheets could be excellent. Okay, so there are examples, real life examples, which we can very easily access, which we can very easily locate and make measurements of. Graphite is very easily located you can easily get a piece of graphite of various qualities from various different vendors, and this is easily noticed. Okay, so the point we need to I want to draw your attention to is that real life materials which we can very easily get our hands on often display significant anisotropy, not just marginal anisotropy but significant anisotropy. Why is this of significance to us? It is of significance to us because if you look at even our new model, our improved Drude-Sommerfeld model, where we have replaced the Maxwell-Boltzmann statistics by the Fermi-Dirac statistics. If you look at our improved model, we still do not have anything in this model to suggest that there will be any anisotropy as of now. Okay, as of now, where we have come, where we have simply replaced the Maxwell-Boltzmann statistics by the Drude-Sommerfeld, by the Fermi-Dirac statistics. At just this stage, nothing has been incorporated in this model which suggests any anisotropy. So yes, you may get a better value for the specific heat at constant volume or the electronic contribution to specific heat at constant volume, but it still does not explain to you why conductivity should be better in one direction and should be worse in another direction, right? It does not explain, does not even give you a hint, does not give you any possibility of any anisotropy. So this is an issue that we are now faced with. So as we just the way we looked at the drawbacks of our first model and we improved it, we now recognize that in our improved model, in our first step at the improved model where we just changed the statistical distribution, while we have made some progress, that alone is not apparently sufficient. Okay, so that alone is not apparently sufficient. There are additional features of material properties which are not being captured by our improved model, right? So that is the first thing that we wish to recognize, make note of, and therefore act upon. Okay, so this is where we are. So now what can we do? So what can we do that will enable us to now start introducing some of the introducing into our model features that enable us to capture this anisotropy, right? So this is something we have to recognize. Now where does this anisotropy come from? I mean, to some degree we have to recognize the fact that the way the ions are arranged through that solid, it results in some periodic structure which results in planar spacings of a certain kind in different directions and so on. In our model we have not accounted for this in any way, we have completely ignored it. okay. So in fact we have completely ignored the ionic course. So and we have in fact said everything is averaged. So that is where in fact we have sort of knowingly or unknowingly enforced isotropy, okay. We have enforced isotropy into our model by saying that it is a free electron model, it is a free electron cloud, everything is sort of uniform, and therefore the electrons do not experience anything different from location to location, okay. So without specifically aiming to do so, without deliberately aiming to do so, we have somehow ended up creating a situation where fundamentally the environment of that the electron experiences is isotropic, because everything has been averaged out, therefore its behavior is isotropic, therefore the material property that we measure is isotropic. So fundamentally down in a very first step we have assumed isotropy, and therefore it is not surprising that our result is also isotropic, fine. So that is the thing we have to recognize, we have assumed isotropy, that is why our result is isotropic. If we recognize that in fact at the at the atomic level or at the crystal structure level things are not isotropic, then perhaps in our final results that will begin to reflect in the property and the ability of the property to also remain isotropic or anisotropic, right. So therefore the specific point that we now narrow down to is that we have to have a better picture for what is the potential that an electron experiences through the extent of the solid. It is not enough for us to make the approximation that everything is averaged and it is okay to stay averaged, okay. So we have to recognize that it is not an average potential, there is from location to location possibly the electron experiences different potentials. So we would like to incorporate into our model the dependence of potential as a function of position in a crystal, okay. So potential as experienced by an electron, okay. So an electron passing through the crystal, now we have to incorporate into our model the fact that as an electron passes through the crystal or moves from one end of the crystal to another end of the crystal, in its path each location is not necessarily exactly the same as other locations, every location has some differences in terms of what it is trying to do, what is the interaction that the electron is forced to have with its immediate surroundings. So this detail we have to incorporate into our model and then see if in what way we can incorporate this detail, to what degree of detail we can incorporate this phenomenon, and therefore what is the impact on the property of the material, okay. So this is what we will attempt to do. So now let us take a look at at a single let us look at a particular ion, okay. So let us say that this is the location of an ion, okay, physical location of an ion. So this is I will just say this is Ag plus, okay. Now independently I will say this is the axis of position and this is potential, and I am only making use of this position of this atom is here, fine, or this ion is there, fine. So that is where it is, and so this diagram has not got anything to do with the axis, we are only interested in this position, so I have just marked that position out here. Now if you take so this is zero potential energy, fine. So this is a positively charged ion and it is located at this position, some position x here, and we would like to get a feel for what happens, what is an electron experiencing as it comes from infinity close to this position, okay. It starts off at infinity and it moves towards this position. When you do that, what is the electron experiencing? Now when an electron is at infinity and let us say that we have got enough distance here that we are headed towards infinity this side, when it is at infinity with respect to at infinite distance with respect to the position of this ion, it does not experience any force of interaction with this ion, that is the definition of this of it being at infinity, okay. So as you tend towards infinity, the potential of that electron tends to 0, it is free, it is truly free, it has, when it is free the potential around it is 0, it can do whatever it wants, it can go up, go down, any which direction, there is no preference, nothing is pulling it in any direction, and it is free to go wherever it wishes, okay. So we just use this as a guideline for the position. Now as it comes closer and closer to this ion, because this is positively charged and that is negatively charged, the potential energy becomes more and more favorable for them to get closer and closer. Okay, so the attraction forces of attraction are there, and so the potential energy keeps going down, fine. So it becomes more and more attractive. So in general you see a tendency to of the behavior to look like this. Okay, so this is the potential as a function of position for the electron coming from say minus infinity towards this location x, fine. So this is what is occurring here. Now if the same thing could hold true from coming from the other side. Okay, so you start at positive infinity and you move towards this ion, then the same thing would occur. You will start off at 0 somewhere at positive infinity, it would stay at 0, and as you get closer and closer to this ion, in a very symmetric manner it will do this. So this is the potential as a function of position that the electron experiences as you come from either minus infinity or plus infinity towards the position of the ionic core. Okay, and this is I am taking a one dimensional case. In principle you can do this in 3 dimensions, I am just taking a one dimensional case because it illustrates our point, that which is all we are interested in. So this is the with respect to a single ionic core, this is what is happening. Okay, so when it gets very close to the ionic core, it will start experiencing the electronic cloud of that ionic core also, but that is something that we will not really worry about at this stage. It is just that they are coming, it is coming from far off, and this is the potential that it is experiencing. Okay, so this is with respect to a single ionic core. Now we will extend this, we will make a one dimensional lattice. Okay, a one dimensional lattice where ever so periodically you have an ionic core. Okay, so we will do that to see what is a realistic what is more realistic in terms of what is it that the electron experiences as it moves from one end of a crystal to another end of a crystal. So we are taking a path which involves a series of ionic cores. So it is a single line of ionic cores, and along that line we are moving that electron. We would like to see what is the electron experiencing. Okay, so we will see here what it is experiencing. So I will just say we have for simplicity's sake I just taken 4 ionic cores. Let us just say that we have 4. We start from this is potential, and this represents the positions of those ionic cores. Okay, so the positions of those ionic cores. So this is potential, position. Fine. So we come from we will just put the guidelines down there. As we can expect, whatever we described for a single ionic core will be true for each of those ionic cores. Okay, we will say that it is a one dimensional lattice that we are interested in, and so that our discussion is focused on a one dimensional lattice, and for simplicity's sake it has to start somewhere. It is a finite lattice. Okay, so there is only a certain finite number of atoms there, it is not an infinite lattice. So it is a finite lattice, and for our simplicity's sake we have stuck to 4 ionic cores so that we can at least see what it is that we are trying to illustrate here. So around this around each of those ionic cores, if you take each of these ionic cores independently, okay, independently and look at them, then what I just described will hold true for each of those ionic cores, right. So there is nothing that distinguishes one ionic core from the other, nothing that distinguishes one electron from the other in terms of behavior. Therefore their interaction is going to be exactly the same. So for each of these ionic cores, in principle we can draw the same kind of diagram that we have just drawn, right, except that these ionic cores are within the are actually inside the material, whereas this is the one that is at the outermost limit and that is the one that is at the outermost limit. So therefore when we actually sum up the contributions, there will be some changes. So first we will draw as though they are independent, then we will see what is happening because they are not independently existing, but they are existing next to each other in a crystal. So if they are independent, then we see this behavior. I will just put it as dotted line initially. And this occurs as we go towards plus infinity. So it's I mean we need not, I don't want to mislead you here. So we will just say that goes that way. Similarly for this ion you will see a behavior that looks like this. For the next ion you will see a behavior that looks like that. Okay, so we now see that for each ionic core we can think of it as a potential well. This is called a potential well. So it goes at as the electron is at far away from this first ionic core, there is no it is not experiencing any potential, so it is free, so the potential is 0. Okay, so potential is 0 here. As it gets closer and closer to this ionic core, it experiences a potential well, where its potential energy decreases very sharply as it gets closer and closer to this ionic core. So independently again as you move away you see the behavior following this curve. For this ionic core these are the two curves of relevance. For the third ionic core these are the two curves of relevance, and for the last ionic core these are the two curves of relevance, but behavior is essentially exactly the same. So for independently for these 4 ionic cores we have seen what are the what is the behavior that the electron what is the potential that the electron will experience. Now we recognize the fact we additionally have to incorporate the fact that these are not independent ionic cores, but they are sitting at fixed positions with respect to each other, okay, and they are in a single in a crystal together, right. So therefore an electron that comes here will experience this potential well coming from infinity, because there this is the first ionic core that it is experiencing, right. Now as it starts moving away from this ionic core, up to this point its potential energy keeps increasing, but beyond this point it is actually beginning to see the potential well of the next ionic core, right. So therefore it will now instead of just going off to plus infinity, it will actually have to instead of going off to 0 as you move away from this ionic core, we have to account for the fact that as you move away from this ionic core you are actually getting closer to this ionic core, right. So therefore the potential of this ionic core will take over, then you will come out of the potential well of this ionic core and you will enter the potential well of the third ionic core. The electron will enter the potential well of the third ionic core, again it will come out of that potential well of the third ionic core, enter the potential well of the fourth ionic core, and then after the fourth ionic core as you move away there is no further ionic cores this side, potential can go back to 0, fine, as you move further and further away towards infinity, so it can go back to 0. So therefore the resultant behavior that you see is what I will draw with this with now the complete line. With the solid line, okay. So an electron now traversing through this one dimensional crystalline solid which has ionic cores at these specific locations actually experiences a potential versus function that looks something like this. It is 0 when you are far away at infinity with respect to this entire one dimensional crystal, then it experiences the first potential well when you come close to the and this structure is called a potential well because it's a well because it is deep, and it is not, it's a well of potential energy, that's what it is. So that is why it is called a potential well, okay. So potential well exists in this region. So that is the potential well, okay. So that is a potential, each of them is a potential well. So potential goes towards sharply drops as you come close to the ionic core, again goes up as you move away, then falls into the second ionic core, comes out, goes into the third ionic core, falls into the fifth potential well, the fourth potential well, and then comes out, okay. So so this is potential versus position, okay. So we will just redraw it for sake of clarity. Potential or energy it is, okay. So it is basically the same, potential or energy, and this is position. So we have, if you only plot the solid lines and not worry about the these are just for guideline for our plot. So we have a behavior that looks like this. So this is the potential versus function, I am sorry, potential versus position for this system that we are looking at, fine. So now therefore for our analysis to become more complete, for our model to become more complete, we have to accommodate for the fact that as the electron moves through the solid, it is not actually seeing an averaged response from the entire crystal all the time. Rather there is a specific feature to the whole potential energy versus position that it is experiencing. Therefore as it moves through the crystal, it is forced to interact with this phenomenon, with this background. The extent of interaction may vary, okay. So but this background is a reality. This background is a reality that it cannot completely ignore. Depending on where it is, it may be more significantly affected by this background or less significantly affected by the background. So that is the extent of its impact on the electron can change, and we will look at that. But what we are recognizing at this stage is that into the model we have to build enough sophistication into the model, enough detail into the model, that this information is getting incorporated into the model, okay. So that is the thing we have to do. Now having said that, the features that we see here, if you wish to put it all down in equations and so on, it can get a little bit complicated in terms of this exact level of all these features. Even though I have drawn these ionic cores independently, the second, the third, the fourth will also ionic cores will also impact the exact form in which this curve changes, okay. This curve moves or the shape of this curve is not going to be impacted only by the outermost ionic cores. It will have some contributing factors from all the other ionic cores and so on, plus the fact that this is the surface. So the exact shape of each of these lines is something that needs a lot of calculation before you can actually say that this is the exact shape of that curve. So it turns out that for our purposes, in fact, that level of detail is not immediately necessary. So in moving forward from with these models, while we will incorporate the basic idea that this figure is conveying to us, it is not immediately necessary for us to incorporate it in exactly the form that you are seeing on the board, okay. So we will approximate this form, we will make an approximation of this form such that that approximation is something that we can work with, that we can make calculations with, and we so that this form is actually being incorporated, and therefore the model is definitely getting more realistic because it is now looking more and more like the real material. At the same time, it is not so complicated that it makes the calculations impossible. It makes the calculations reasonable, it makes the calculations possible, is the kind of approximation that we need to make. So what we will do is, instead of having all these curved lines that we see here, we will convert them to some sort of straight lines which still captures the basic idea of this picture. So I will just draw that picture, then we will explain it, okay. So we will we'll look at the explanation of it. So same thing we will look at. I will assume the same lattice positions here. So in terms of lattice position, I am not going to change anything, I am going to leave it as it is. So in that sense the reality of the actual material is captured, nothing else I am changing there. This is 0 in potential energy, and this is position, so all of that is still the same. What we will say is that at infinity it is the potential experienced by the electron is 0. So I will just stick to this x axis here, okay. Then I will say that there is a slight potential well here, so this picture here is now being approximated by this picture here, okay, where we are saying what are the features that we are capturing. We will just look at what are the features of this picture that we are capturing here and what is the approximation that we are actually making, okay. The features that we are capturing here are that as the electron is far away from this set of ionic cores, okay, so the ionic cores are here. As the electron is far away from the set of ionic cores, the potential it experiences is 0, okay, and therefore that is 0 here. At some point as it approaches this ionic cores, the potential that it is experiencing from those ionic cores starts becoming significant. So at that point there is a drop in potential of this electron, potential energy associated with the electron as it comes towards the material, okay. Then as it gets closer and closer to an ionic core, there is a very significant drop corresponding to this drop here, which represents the potential well that is very close to the ionic core. Then again in between the ionic cores there is a rise in potential energy, and then again a drop into the next potential well, rise in potential energy, drop into the third potential well, rise in potential energy, drop into the fourth potential well, and then as you move away, since there are only 4 ionic cores in our example, as you move away from the last ionic core, you eventually reach a stage where the impact of these ionic cores on that electron that we are looking at becomes negligible and can effectively be treated as 0. So we have taken the electron away from this material far away enough that it no longer interacts with this ionic this system of this collection of ionic cores. So in that sense we are capturing all the detail of this picture here. This is the more real picture. From this real picture we have made this approximation. Much of the interaction that is that is shown in this picture has been captured in this approximation. The only real difference that we have done is these are all curved what shall I say, curved lines, so to speak. So curves that we have here, we have approximated them by straight lines, okay. So these are also referred to, since they are straight lines and they are parallel lines, we call them square potential wells, so to speak, more squarely shaped potential wells. They are not exactly more rectangular, I guess, but the fact is that these are potential wells that are based on straight lines that are parallel, okay. So the width of these potential wells is fixed, whereas the width of this potential well is actually is changing with position marginally. So this we just have a narrow deep potential well of a certain fixed width, and that is what we do in all of these potential wells, okay. So there is in terms of the exact form of the potential well, we have made an approximation, but we have captured the idea that there is a potential well, that it is centered around these ionic cores, and that there is a feature to this whole process, that you come from infinity, there is a drop in potential as you get close to the material, and there is definite potential wells around each and every single ionic core. So very important pieces of detail corresponding to this real picture have been captured in this approximate picture, and we have made some simplification in terms of the exact shape of the well. That simplification will enable us to make the calculations much more effectively. So that is why we have made those simplifications, and of course it is left for us to judge later based on our results whether or not that simplification was acceptable, okay. At the moment we have made the simplification. If the results indicate that our simplification was reasonable, great, that means this is a very good way of approximating the solid. If for some reason it shows that our approximation gives very wild answers, then we will have to re-examine this. I mean, I might as well just tell you upfront that this is a pretty reasonable approximation. This is considered a pretty reasonable approximation, so therefore we can use this. Also in the context of this picture, I also want to point out that when you say when the potential is 0, that is the same as saying that the electron has escaped the material, okay. So it has escaped the material. So when you do say when you see photoelectric effect, okay, so when you say an electron has been ejected from the material, then you have actually gone to potential being equal to 0, that electron has truly escaped the material. So being in this region or being in this region means that the electron has escaped from the material. So that is a truly free electron. So so far we have used the term free electron and free electron cloud. Strictly speaking, you cannot call them free electrons because they are still within that solid, okay. So therefore they are not strictly truly free electrons. A truly free electron is one that has escaped from this solid, which means the potential it experiences would be 0. Then there are electrons which fall within this potential, this slightly shallow potential well above this level. They are electrons which are trapped within the solid but are not held by any particular ionic core. In fact, what we were referring to as a free electron gas previously are in fact these electrons which are trapped within this material, because obviously they are not running out of the material, they are trapped within that material, but they are not stuck to any one ionic core, they are free to run across the extent of the solid. So therefore these are electrons that we would actually call as nearly free electrons. They are not truly free because they have not escaped from the solid, but they are relatively free because they can run through the solid. So those are nearly free electrons, right. And finally there are electrons which are stuck to the ionic core. Okay, so those are the electrons which belong to part of that ionic core. So those are referred to as bound electrons. They are the electrons that are part of the ionic core. They are all the other electrons which are stuck to that Ag plus ion, so to speak. Okay, so those are the bound electrons. So electrons that are in this regime are bound electrons. Electrons which are here are nearly free electrons, and electrons which are past this point are truly free electrons. Okay, so so this is the picture. In the next class we will start once again from this picture, and we will look at some of the nuances of this picture, and we will relate whatever else we have discussed so far and see what it means with respect to this picture. Okay, and then see how we can utilize this picture. We will see what does say Fermi energy mean with respect to this picture, what does work function mean with respect to this picture, and so on, and then utilize the and in that way relate whatever else we have discussed so far with this picture, and from there on we will take it forward and utilize the features of this picture to modify and improve our models of the material, and therefore our understanding of the material and how it behaves. Okay, so with that we will halt for today. We will take it up in the next class. Thank you.